So, okay, let's get started with the next lecture in the machine learning techniques in structural mechanics. First of all, I get a question regarding, let's go a little bit side about and talk about the projects and home projects. I get a question regarding what is a main project and how the main project is related to home projects. So the system is the following. You will have 3 home projects. You already had one, and we already even discussed that. You right now have one about cracks detection, and we will also announce the third one, I think, in a couple of weeks. What we want for this small project, the home projects, we just want you to have some hands-on experience in coding and in sort of designing the specific neural network architectures. At the same time, we want to see also one sort of main project, when you not only just do coding, but also give some sort of report explaining what you are doing and explaining why, let's say, this particular architecture is selected, why this particular number of layers, and what will happen if you will increase number of layers, and so on. Also, you need to a little bit discuss the problem itself that you are trying to solve. So it should be one only big project, and you either can use one of the 3 home projects that we give you, or we will give you as a basically backbone of your project, or you can come up with any other ideas and just, in this case, talk to us, please. We will see if your idea is reasonable, if the things that you would like to do as a project is reasonable, and then actually we will support you a lot, much more than, we will be very interested in seeing how you progress with your own specific task, rather than just doing the things that we provide you. So we are always open to help you and to give you some feedback regarding some sort of project that you want to do. So that's the rules. So what we want to see, we want to see 3 successful let's say Jupyter notebooks for 3 projects that we give you, and we would like to see one larger project with report. Is it clear? Like, I think I already a couple of times discussed that, and now I hope that it's clear. So now let's go back to the lectures. Today's lecture is a little bit, let's say, ad hoc lecture, because I hadn't planned to talk about the topic that we will discuss today. But considering this realization that not all of us have good backgrounds in probability theory, I think it would be quite unreasonable to talk about more advanced things like Bayesian optimization. So what we decided with Gerrit, we decided to maybe discuss it a little bit at the very, very end. And instead of Bayesian optimization, we will talk a little bit about the topic of recurrent neural networks. Right now, maybe they are not so popular, but they still can be applied in many fields. Even in structural mechanics and in structural health monitoring, and you will see that at the end of this class. But to be honest, if you compare them with just classical multi-layer perceptrons, like this deep neural networks that we studied, and or with especially with CNNs, they are not so popular right now. At the same time, next lecture, or next actually 2 lectures, we will talk about super top-notch research in generative neural networks. And that's something that you definitely would like to hear, would like to see. And the next time, Gerrit will give a lecture next Monday regarding generative neural networks, since it's his main research direction. And then probably the week after, we also will discuss a little bit of generative neural networks in application for material science and solid mechanics. Right now, it's really, really hot topic, and I really waiting. I anticipate to share this topic with you. But today we will talk a little bit about maybe more boring stuff, but at the same time, it's still interesting in my opinion. So let's start. So first of all, as usual, we will start with a recap of the week 7. So what have we learned? If you remember, we talked about transfer learning, and this Thursday you will have an exercises, right, Gerrit, with the transfer learning. So you will use it by yourself, and I think you enjoyed last Thursday to play with YOLO models that we studied last week. So that would be also quite interesting experience for you to work with transfer learning. So we formally define such terms as domain and tasks for transfer learning. We learned that transfer learning is a very powerful tool enabling us to utilize pre-trained model and save a lot of time. We also now know and understand different types of domain adaptation. In many cases, we learned on the example of, let's say, ant tracking, that it's possible to use synthetic data generation via simulations in computer, let's say in game engines, and then transfer learn models to real world. Finally, the last couple of minutes of the last lecture, we talked about CMS networks that enable an efficient solution of classification problems via similarity learning, and that I think was a very interesting topic as well. So, what if we try to think about previous models and previous architectures that we learned? So let's talk about multi-layer perceptron models like deep neural networks and CNNs. So when we work with them, what happened actually is the following. So we give the image to our pre-trained neural network, and the image tells us, okay, this is a cat. We give another image, and neural network tells us, this is a cat. Finally, another image, cat. Or if we look at our YOLO task that we did last week, we look at the image, and YOLO tells us, okay, there are cars, trucks, and other objects, and also we have the detection, like the positioning of these objects. So our input elements in this case are quite independent. And I think some of you asked me a question during the practice regarding the video processing. So can you tell me what's the difference between, let's say, video and image? So set of images, different images, and a video. What is the fundamental difference between them? Yes, exactly. So in video, if you take the video, each frame kind of depends on the previous one. So in just random images, it's not a case. And what we've done before, until now, we actually played with just individual inputs. So we never thought and never tried to work with the sequences. And that's something that we really want to do, because sequences are really important, and we feel that if we process image as a sequence, we can get much more data, much more information, and much better tracking, let's say, in comparison if we do that as just each frame is independent image. So okay, there is a good example of the video as a sequence. When also do we have sequences as inputs? What examples can you give? So in which cases we can talk about sequence as inputs? Any ideas? Interesting. And I would agree with you. I would agree with you that, let's say, stress-strain curve may be described as, let's say, we have sigma and epsilon. Again, if you don't know, it's like displacement, and this would be force. Something that looks like that can be kind of defined as a sequence of the points during the loading. It's usually not so often, but I guess there are some manuscripts that deal with that. It's not a good approach, honestly, for the stress strains. But again, beside, like if we put beyond structural mechanics, where we see the sequences. Okay, video. Where else? Audio, absolutely right. Even playing the notes. Notes, it's actually sequence. Each note individually doesn't make a lot of sense. Notes start to create a music when they're in a particular sequence. But even more often, like the sequence that you see every day. Even on this screen. Come on. What? Okay, traffic. I would again. You can play this as a sequence. It's really hard to argue against. But come on this screen, you see sequences. No, let's go simple. No, someone else. Yeah, I want to hear a text. The text is a sequence. Come on, you have the words that actually go in one by one, and they're still connected. Each individual word actually doesn't make a lot of sense out of context. Context matters, sequences. So yeah, that's exactly signal in general. Let's say you have the signal from the sensors. It's a sequence. You have the text. Text is probably the most well-known and studied sequence, especially in relation to machine learning. And again, video that you already mentioned. Okay, that's really cool. So right now we at least know 3 different types of sequences. And of course, I would say from the structural mechanic perspective or from the civil engineering, signal is only one of these sequences that would be interesting for us. And again, the paper at the end of the talk will show that. But now, since we're talking a lot about, we'll talk about RNNs, we'll see that. We'll talk mostly actually about the text. So, but now, okay, now we know it's sequences. What tasks can be handled, can be performed using sequences? Any guesses? So, okay, if we have a text as a sequence, so what we can do with the text? Any ideas? Come again? Yes. Let's say that in this case, if you have the video as a sequence, you can create the text as another sequence as annotation to the video, and you can train your model to do that. But even probably easier to understand, it's actually speech recognition. You have a sequence of sounds, and you transfer it. You train your model, and it's done already. Like it's right now one of the top-notch research as well. You can really transform it to the text, annotating the YouTube videos and everything like that. It's really useful thing. What else? So you are saying, can you repeat? Instructions. What do you mean by that? Again, can you go a little bit deeper? Yeah. Yes. Yes. That's yes. That's basically, again, you can create sort of one of the things maybe very similar to what you're trying to describe. It's a summarizing of the text. So you have the big book, and you train machine learning to just shorten the context and just give you a summary. And this is right now, again, what ChatGPTs and all these models are doing. They really can do that. So, of course, besides of that, we also can say about, okay, let me just write it down. So one, I will probably do it with, so what became video annotation. Text summary. I have no idea how to write it correctly. So I will say summary. Nice. Let's say what we also, for the text, actually, almost all these models, like we will talk about, they were created for specific task related to the text. What do you think this task is? Come again? before chatbots. Chatbots are also kind of important, but like chatbots, it's a little bit like just you playing with that more or less, but very important task related to the text. Yes, but it's not so related. The main actually task is translation. Language to language translation. That's a whole idea behind all these models, and actually development in these models. You cannot separate them from this development of the translation. So text translation, it's one of the cornerstone ideas. And again, if we go further, we can say something like music generation, because you also can generate sequences. And there is another probably example. Okay, yeah. So I will go with an example that I like, sort of DNA sequence analysis. Nice. So if you know that we have this, I don't know, I remember AT, what else do we have? No, not, yeah, all this four, I mean, DC? G, yeah, G, yes, I thinking that, oops, sorry. So, and then you kind of combine these letters in the sequences, and each sequence can correspond to different protein. So again, actually, there is a lot of sequences around us, and there is a lot of demand in developing the tools that can handle that. But at the same time, I would say the main thing is connected to the text, and that's why in many cases, what you see so-called language models things. And I decided, okay, I will ask ChatGPT, why do we need language models? And the answer is the following. So there is a couple of reasons why do we need language models, natural language understanding, because actually in many cases that's a very demanding thing. So as an expert in some fields, you can easily let's say, program something or create something that you can understand how to use, or your colleagues will understand how to use. But if you just ask a regular person, you really need to give a very, very detailed instructions how to use specific machine or specific tool. So like, you know why IKEA in particular is very famous, because you always have a very detailed instructions how to assemble your, I don't know, yeah, whatever you buy in the IKEA. So again, text generation is highlighted, and I think this is quite important as well. Again, we cannot miss the language translation. It's one of the very important stuff. Speech recognition, we already talked about that. And this is, again, information retrieval and extraction, things we discussed like a minute ago. So then I said, okay, since we are doing things associated with structural mechanics, I decided to ask to where in the field of structural mechanics and actually civil engineering it's useful. And to be honest, this is okay field. I think this is something that we even can discuss it. So that helps us to understand a lot of technical documents and maybe create some summaries. Again, things that we discussed. Knowledge discovery, it's quite challenging task when you try to analyze already existing literature and discover something that is not covered that yet. So you see some connections between the different documents and then see, okay, there is interesting correlation that no one was able to pick it up. So, and the computer will help you to do this new discovery. Structural health monitoring, again, the things that we discussed in the context of sensors. Again, design assistance and code generation. And finally, what I say, okay, since we are interested in application for the structural mechanics or civil engineering, what are the ways to utilize it in structural health monitoring? And again, the same honestly questions, same replies, data analysis interpretation. I like this anomaly detection and pattern recognition. We discussed that in context of CNNs, but you can really use sequential things because when you do health monitoring, it's usually not one measurement. It's just usually long-time measurement, and then you need to see the patterns in the behavior of your structure, and that's really useful. And finally, we have so-called decision support systems. It's really sort of also analysis of the data, but maybe in this case more a little bit of like complex analysis of whole data together with not only sensors but also with the text and different documentations and different again maintenance strategies, whatever, so protocols. And finally, again, of course, to help with the creation of the university courses. So it allows me to write that and discuss in details what ChatGPT suggests as a good application for language models. So now the question is, okay, we go back to the text. Now the question would be for you, how do you think we can encode the data? How can we encode the text? So let's say we have a text like that. Students of ML class have bright, I think don't need a bright future. Now, since our models, our, I don't know, computations in NumPy or cannot deal with the words, for them words do not make any sense. What would be your suggestion how to store this sentence in a memory and then process it? What would be your suggestion? Any ideas? Oh, yes, but that's more or less translation to the binary system. Okay, in this case, you will see something like 0011, I don't know, 2, then, or maybe in Unicode or whatever. You cannot really nicely work with this thing in NumPy. So it's, again, this is just another way to store the string. It's another way to store the array of chars. What method would you suggest? Okay. Okay. Yeah, okay. That's much closer. All you actually not so far from the truth, but actually how they're stored originally, at least right now there is a little bit different ways. It's using one hot vector. It's very inefficient when you look at that. So the idea that you have a dictionary and dictionary contains all words that you would like to actually in general use. So let's say 10,000 words, it's usually quite a lot. And again, it starts with A and ends with, I don't know, what's the last word in the English? I don't know, Z something. Actually Zulu, I think. There is, at least it's, and then again, you have the index. So 0, 1, 2, 2, 2, 2, 2, 2, let's say 10,000, right? And each of the words that you see here, it's stored as one hot vector. For instance, word student, if we assume that somewhere here we have a student, and let's say at the position 5,000, I don't know, 333, what you will see, it's 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. And this is the word, this position, number 53333. So it looks quite inefficient, and actually it's not very efficient. I agree with that. But that's how you store your words and sequences. In this case, sequence will look like that. So what I will do the following notation. So this would be first element of the sequence. I will say x1. This will be x2. And so on until x 1, 2, 3, 4, 5, 6, 7. X7, right? And in this case, my x1 would be 0 to 1 on this position 0, x2, and so on. Is it clear how we store the data? Again, one hot vector. That's best that we have right now. So, and with that in mind, now I ask you, why cannot we use just regular deep neural network? Why cannot we take this, let's say, sentence? We had 7 words, if I remember correct. 1, 2, 3, 4, 5, 6, 7. Just feed it to some layer, then feed it into another layer, and then get some output that we want. Why do you think it's quite bad? Why do we need decoder? For instance, what we, let's say what I'm doing right now from this task, I do so-called sentiment analysis. Yes, it's called sentiment analysis. Yes, sentiment classification. So, you know, you read the review on Amazon or eBay, and you just want to understand if it's a good review or bad review just by looking at the text. If someone's saying, okay, this is amazing, I don't know, laptop, you say, okay, this is good. So you actually classify it as 1. And if I'm saying that this thing is broken after 2 openings, or after, I don't know, I just drop it from the stairs, that's bad review. So that's your task. You don't care about the decoding right now. So why do you think for this task, this particular architecture is bad? Then you train this. You can tell you feed these sentences with your labeled data set that you label by yourself, and then train network like that to predict based on input: is it good review or is it bad review? So what do you think the problem here? It's one of the reasons. Yes. Can you then elaborate? Yeah, but you have all of them. You have all words, like in this case, this laptop is very, very, I don't know, very bad. So let's say like that. So you have all words from this one, and you kind of can train it, technically speaking, to say, okay, this is bad review. Despite the words very, the bad in this case will get a lot of weight during the training, and then you will be quite confident in predicting that this is a bad review. But you are close. So what do you think the reason? I would actually agree with you. I will give it to you. So the thing is, it's in particular associated with this your point. The fact is that this neuron, input neuron, is actually absolutely independent of this neuron. They really do not do anything together, technically speaking. Like, sort of course, at some point their weights will be combined. But the thing is now, what if I will say this, I bought a very bad laptop has been bought. So I just changed the order. Now word bad will be somewhere here. And since this neuron is actually expected to, it doesn't expect to know the word bad. It actually was trained more or less on like the very. So the thing is, it really doesn't matter where this word bad appears. If you see the word bad, in many cases it will mean bad review. So therefore, it's quite useless to train it only on this position. So you somehow need to really train that everywhere. So you understand this, what the problem is? So because in these inputs, it's like what you did with. I didn't do that. Yes, we did with only coordinates. For instance, if you predict the classical example, the price of the house, and you have the area, and let's say you have the number of stores, so area is something between, let's say, 50 square meters to, I don't know, 400 square meters. A number of stores is something 1, 2, or maybe in an extreme case 3. So in this case, you have one neuron that trains for the area and one neuron that trains for the number of stores. And when you train them, then you cannot switch them like that. So you cannot say, okay, now I put number of stores here and area here. You will get absolutely absurd results because, again, each neuron, in this case, each input node has its own sort of purpose. In the text, it's not like that. In the text, you can actually play with the positions. Therefore, it's actually quite bad. But another thing that is not very, that you haven't noticed, that the text can have a different length. What we did before that, we've worked with only the same number of inputs all the time. But the text, the sentence, or the review can have a very different length. And therefore, two main problems with the classical architecture here is its inputs and outputs can be different lengths. Again, in this case, output is the same, but inputs can have a different length. And also, there is absolutely no sharing information between input variables. Absolutely nothing happens on this input layer. So that's what I talked about just a minute ago. So that's a problem. And therefore, in order to solve this problem, what we came up with is so-called recurrent neural networks. And it looks quite interesting. So the idea is the following. So you have, okay, no, it's too high. You have your first element of the sequence. And then you have some layer with the weights or all the stuff that outputs the first output. Again, in this case, let's say we are doing translation, like trying to do word-to-word translation, or we're just doing some operations on the text. So then you have your second input. And you put it through this layer and get the second output. But now the trick, what you also get, it's information from the previous layer. And another trick is actually that this node and these layers are absolutely identical. It's the same layer that just process things. So what actually usually is written here, you get a 1, then this A1 is get transferred to A2. Here it's get transfer further to, and then you do that until the end of your sequence. So it's called TX, and you have. So, and sometimes you also have this 0 input contains only zeros, just to have some initiation. So let me just check that I'm correct in my drawing. Absolutely correct. Absolutely right. So one thing that I probably need to do, since it's predictions, I would like to put hats there. And oops, what happened? So, and sometimes what is done, you just, in literature, you may see something like that. T, Y, T, and then some sort of loop. So this is the same thing that just repeats over and over again, but just accumulating a new elements of the sequence, but knowing the previous elements of the sequence. And that's a trick in terms of processing of the sequences. Now, your inputs are not independent. Your next input knows about what happened before. So when you process this new input, you have some information about the what previously happened. Okay? Just let me see. Yes, okay, that's fine. So in this case, what's important that all these blocks, I just will do that. Are identical. Again, this is something that somehow can remind you a little bit CNNs. When we, instead of just unwrapping all our images in the pixels, we really just played with the filters. Because we know that pixels nearby are they kind of interact with each other. But the pixel in the left top corner and the right bottom corner probably quite independent. So we are using something similar here. So this is how it's usually, oh, there is a mistake. So something that you usually see, so again, this is the same thing, but just drawn nicely by me. And what problem? Okay, do you see any problem here? Yeah, actually, yes, okay. I think there is a problem. Do you see any problems with this approach? If not, we will continue, because I actually have no idea what was the point here, but I know that what will be the point on the next slides. So if we would like to write it officially, more or less mathematically, that's how it looks like. So what happens here, each element is getting the previous input. So let's say A3 will be equal to what is G in this case? It's just our nonlinearity. It can be, usually it's actually tangent, hyperbolic tank, or it can be actually in ReLU in some cases even. So again, we have nonlinearity. You remember that there is nothing fancy happening. Then we have some weight matrix, because each of these layers actually has some matrix that is getting multiplied by the previous input. So this matrix, okay, I will probably do a little bit nicer here. This weights is the weights that allow us to calculate A from the previous A. So that's why it's AA index, okay? So it's some sort of weights here. Then we also have the weights that take our input here. So we also multiply this input by some sort of weight. In this case, it weighs X. And we add some bias. And therefore, we can actually calculate the thing that propagates from the one instance to another instance. So that's our A. And then on the top of this A, we can apply nonlinearity. And it can be different nonlinearity, let's say G prime. And it can be softmax. It's usually actually softmax. That also takes some matrix, again, based on this prediction of A from the calculated So I just, for some reason, decided to repeat the same formula. But do you see how does it work in general? Do you see what's happening here? So let me draw it. You will see another way to represent it, and I think you will understand it even better. So what's important for, let's say you have a block. What's important for this block is what's happening from this side. And here you have the matrix VAA. What's important is what's happening from this side, and you have this matrix VAX. And when you compute something, and what you compute is this intermediate value of AT, then you put this value on the right, but also then you use another matrix and another nonlinearity in order to calculate your output. So there is no magic. So it's really just a little bit more computations because you have more matrices, because you have more weights in this case, since your weights right now do not work only with the input elements, but also with the previous information. Again, nothing fancy. Bias goes here. You have two biases, as you can see. One bias allows you to calculate A, and another bias that calculates output. Yes. So in this case, okay, I would say bias of A somewhere here, because it's combined for input, and some bias for Y is here. So again, just follow the formula. Formula are extremely easy to understand what's happening. You really, as inputs, again, here you have. Not so sure. Okay, that's better. This is your inputs, and this is sort of goes from here. So nothing fancy. Again, multiply by weights, apply nonlinearities, get results. So there is a little bit of trick. How usually you will see it's written down. In order not to write this VAA and VAX, what you do, you create the matrix by just merging the two matrices together and merging two vectors together. This notation that you see here is just a long vector when first you write your A vector and then you write your X vector. So because this is a way to combine matrices. So you have one matrix, then you just really attach another matrix on the right, and mathematically it will be correct. So in this case, you can just a little bit simplify things by removing the secondary index. So you have only one weight matrix for all inputs and one matrix for the all outputs. Is it clear? Again, this is just straightforward in my opinion. Cool. So what we have, so now basically we defined our neural network. We defined all weights, all biases, all inputs and outputs. What have we forgot to define? Output we more or less defined. We have one sequence and we outputting another sequence. Let's say we have a text in English and we output text in German. That's our Y's would be outputs. So what is important for neural network, especially for training? What have we forgot? Come again? Yes, but no, activation functions we have. We remember them. Again, just maybe one thing that it can be two different activation activation functions. But what? Loss function or cost function. We forgot about that, how we in this case train, but it's super obvious how to do that. You actually, again, you're just doing for each of these steps, you're doing our classical, in this case, binary cross entropy, like if you classify it as 1 or 0. So for instance, right now, the task would be to highlight words that, let's say, that have positive meaning. And then what you want to output is, let's say you have a sentence, I don't know, very, okay, expensive laptop is bad. So you have 4 inputs and you want, okay, right now, let's say we're trying to create our output to say that output is 0 when it's sort of good word and 1 if it's bad word. So in this case, our output sequence would be, let's say expensive is bad, laptop is, again, good, let's say we classify everything that is not bad as good, and bad we classify as 1. So right now we're doing this for simplification. We'll not do translation. Why we're not doing translation? What do you think? Why this particular one-to-one correspondence is better? Why we are not doing translation? Why this example, in this particular example, cannot do that? Okay, because for translation, the order of words can change. Again, we have different grammatics in the different languages, and also one word can be translated as the 2 words. So right now we can have only one output from one input. So therefore, we're just doing very basic task. Let's say saying, looking at the word and then deciding if this word is good or bad according to some standards. Okay, or we also can take a look and say, okay, if this word is noun or verb. That also will work like that. Because why it's expensive? Because it's important, sorry, because in some cases the same word can have a different meanings. and can exist as noun and can exist as a verb. Can you have any examples? Go ahead. Test, yes. Test is quite easy, or I test my car. So now your problem would be just to look at all these words and say, if it's a verb, actually good example. I had hard time to come up with any examples. So that's the task we are doing right now. We're trying to really put a label like 1 or 0 to each word. And in this case, loss function can be easily defined like that. Of course, if we do a different task, it can be much more complicated loss function. But in this case, again, this is our binary cross entropy, and the total loss is the sum of all our losses on each element. Okay, is it clear? Yeah, and this is the simplest example that we can say. So let's say this is a binary cross entropy. Nice. Okay, that's the things that I already discussed for this particular problem. What did we implicitly assume about inputs and outputs? So we actually assume that we have the same number of input elements and same number of output elements. In many cases, it's called many-to-many recurrent neural network. So in this case, architecture is exactly as we draw it. So we have something like that and like that. Okay, so this is a many-to-many example. There is another example, many-to-one. So we have a many inputs, we have a multiple inputs in our system, but we have only one output. Any suggestions? What can it be? Many inputs, sorry, and one output. Anyone except David? Emotion classification, exactly. Again, you have a lot of words. You don't want to output each word, so you're really just at the end. So this is, and in this case, how it looks like that. You don't have this output errors. And at the end, only at the end, you have this output here. One to many. Any ideas what can be done here? Which task can be classified as one to many? Come again? Exactly. That's actually very good. That's text generation or image generation. What you can do in this case, what you can have, you say, I putting one thing in, first word, I don't know, students. And then what's happening, you actually kind of just have output here, output here, output here, and it just generates your sentence. And that's actually what language models are doing, and we will talk about that in a couple of slides. So in this case, actually what's happening, you technically have only first word, but usually you have connections like that. So your previous words act as inputs for the next layer. But no, in generally one-to-many, it's a good example of the, let's say, text generation or music generation or simple tasks when you really just put initial thing and then get something output. Nice. So in this case, the question is, how would you classify our classic neural networks, like what we discussed before? According to this classification, many-to-many, many-to-one, or one-to-many, what would be the proper classification for our deep neural networks? How? Many-to-one. No, I would not say. Yeah, actually, no. Our classical neural networks would be classified as one-to-one. You have only one input. It can be complex input. It can contain a lot of things, but it's not sequential input. You have one input and you get one output. There is no sequencing, nothing. So again, they can be quite complex. Again, you can generate a video or something like that, but it's still one output, one input. There is no recurrent system there. So it will be 1 to 1. And there is another actually thing considering encoding and decoding that sometimes one can see. Another example of many-to-many can look like that. So you see, I have no outputs now. But what happens at some point, so this would be first stage, when we get more and more information, like more and more elements of the sequence, and then we generate a new sequence afterwards. So, and that's actually more often for language processing, because again, if you just translate word to word from one language to another, you will get absolute crazy result. So you really need to kind of to get all sentence and then output another sentence, another sequence. So that's another example of many-to-many that sometimes you can see in literature. Okay, nice, really, really nice. So let's talk about language models. We talk about this a little bit, but what is the main idea in language model is actually the following. So we have our dictionary with a lot of words there. And we have our recurrent network. So, and then let's say we put with outputs. So what's happening, actually, the whole idea of language model is to predict the probability of specific sentence. So you have a sentence, you have a combination of, like you have a sentence as a sequence, you have a combination of inputs, and the goal of language model, it describes the probability to see it. So how it works in general, so you have all words, you put, let's say, the word students here, and then each of the other output here, what you can do, you can say probability of each of the words from the dictionary. Let's say what the probability to see, it's like it's output 1 considering the input 1. Again, this is still conditional probability, but it's just very simple. So, and if you say that the probability of seeing the word, I don't know, cat afterwards, is quite low, because like students cat, it will not make a sentence. So, but let's say probability of the word of, it's much higher, because like usually you have the sentence students of something or from whatever. So, and the idea when you do the training and you're working with that, it's to do a softmax here and predict the word with the highest probability. And then you feed this word there. And then you see what would be the next word. What will be the next generated word after it knows about the students and softmax, and you go step by step. At the end, what actually models? All this model, even these transformers, very fancy things, what they're doing, they just understanding the probability to see specific words at specific locations, nothing else. So it's just really probability. So now, for instance, if I would like to have a trained model that has good understanding between the probabilities of the words and the previous history, I would like to generate a new text. I would like students and then something. So what actually I'm doing in this case, I take the word students, and then I look at the, let's say, 10 most probable outputs, or maybe 100 more probable outputs here. And then I just randomly pick one of them. So, okay, students, let's see, in this case, I used of still. And then I put it as input to the next one. And now again, I select randomly out of 100 most popular, like highest probabilities. And in this case, maybe university. Probably university would be quite high there. I guess university will be in one. So I get university. And then I repeat it again. And I have absolutely new sequence that doesn't exist before, but generated according to language model. And this sequence, if your language model is good enough, should make a sense, because it combines words with the highest probability, that really goes together very well. So that's whole trick about language models. Again, it's a simplification because I don't want to show a lot of math, but that's how it works. So yeah, and now it should be actually here. We can generate new sequences. That's what's important with this approach. When we take some highly probable words and put them at the next layer, we can have a new sequences, new sentences, new music that will, of course, resemble something that already exists. So, and that's how this RNNs work here. And now we can actually generate new sequences, and that's already going a little bit towards generative models that Garrett will talk about later in context of image generation or, I don't know, signal generation probably as well. So the next two lectures will be quite interesting. But for right now, for language models, I think that's what's important for you to remember. So, but we have problems. We have actually quite a lot of problems. That's why you don't see RNNs quite often right now. So what do you think? Are showing this one. What do you think the main problems with this architecture? We already discussed the problem with the classical architecture for these tasks, but do we see some problems here? So here it should be something like that. Any ideas? In general, you repeat it until your sequence is over. So it's like, for instance, in sentence generation, you sometimes have a specific word and dictionary, like sort of end of file or end of sentence. And if you just generate it and pick it, that means the sentence is over. So kind of it's like it's a period more or less. So no, it's not a big deal. Can you identify any problem? Far enough layers barely affects each other. So remember when we talked about classical architectures, when we talked about the dense layers that somehow doing that, and we mentioned a little bit backpropagation. So when we update our weights, just going backwards with the gradients and all, it's one of the first lectures that we discussed. So the thing is, even in a dense layer, you kind of can see in the dense layers that this layer, for instance, and this layer, they are not affecting each other very, very strongly. So because the signal, the information propagates through two more layers here. And this problem is even stronger in the case of RNNs. Because if you have the word, if you have the sentence that we discussed, students of machine learning class have bright future. The thing is, now, let's say the word student and students have the same position, because you usually do not save plural and singular separately. Let's say that they are stored at the same position in the dictionary. So, but now my question is, you have a student here, and then you pass once, twice, 3 times, 4 times, and finally, at the 6th iteration, you go here. And now the question, should it be have or should it be has? Like how this word or how generation on this step knows if you have plural or singular at the beginning. The problem that it will forget about that, because in order to connect this layer, like this layer, to this layer, you need to pass through 5 more layers between, and therefore weight, like if you calculate some sort of effect that this initial layer has on the 6th layer, will be very, very minuscule. So at the end, you have no idea at this point what happened at the beginning of the sentence. And that's a problem. The far enough layers barely affects each other. And in text, it's really bad. Because in this case, your text will be absolutely grammatically incorrect. Because in this case, you can say, okay, has. Because you also store have and has, of course, as the same word in the same position. Let's say the position 100111. Yes, and students, we already know it's something like 5333. And that's a big problem. Again, this is sense. So, and there is a trick, and this is a trick that actually was proposed in 1997. So even before these big breakthroughs in neural networks, because people worked with the text, they worked with the translations, and they saw this problem, and it was a big issue. So this is how we can visualize our element of RNN neural network. You have this input, you have this previous information, you have X as in new input, you output information on the right, and then you process also this information to get our output. And again, this is something that we already know. Okay, so that's what we already know. And here, what I forgot to write, it's again your output is another, as I say, softmax. It will be G prime, something like T plus by. So in order to avoid this problem of forgetting things, in order to try to track something that happens before, there was a new unit proposed. And it looks a little bit hard to understand, but I actually will go step by step with you. First, what happens? You calculate this A exactly as you did before. And then you introduce a new variable called C, in this case C wave. And this variable, it's how it's called? It's I would say probable replacement. Let's call it like that. It's calculated as a nonlinear tan H of another weight matrix based on the previous information, on the previous C in this case, X and BC. Then there is another thing. It's called gate. In this case, update gate, that take the sigmoid function here, and actually that means that it's either 0 or 1. And then your new variable CT is calculated depending on the value of the gate. So if gate is 1, it will take, its gate at least close to 1, it will take this new candidate and say, okay, the new result is exactly as a candidate. Or if it actually will be 0, then this would be 0, and you just keep the previous C. Let's take a look here and try to understand it on the scheme. For called GRU unit, it's called, oh, I forgot how to call it. It's called gated recurrent unit. Your C's and A's are the same, but we right now will separate them because in the next unit you will see the difference. So what happens? You feed it into neural network. You feed it into our unit. And now, instead of just directly calculating softmax, what we are doing, we are calculating this candidate, and we are calculating this gate using two different nonlinearities. Then we, according to this equation, mix them together. So we decide, okay, should we actually do something with this C or not? And then we output that as a new result. So if we updated it, we have a new C. If we say, okay, gate unit is 0, we change nothing. It's really hard to understand according to schemes, but let me just give you an example that we already used. So we have our sentence. Students of, I will make it shorter, class have a very bright future. So what actually happening? We have the first word students here. And at this word student, we will assume that GU gate will be equal to 1. And then our C will be calculated as some sort of function. And then C that we get here, okay, will be updated. So now we have some sort of some value of C according to these rules. Let's say C is equal to something. Now we move to another word, off. And what happens here? We calculate this GU, and GU will be 0. We want it to be 0. Therefore, nothing will happens with our C, because if GU is 0, therefore new calculated C value will be dismissed. because you multiply it by 0. So we still keep this C that we get here. Then we have a machine. GU will be still 0. This unit update gate will be 0. And therefore, we still keep this information about students. We still didn't rewrite value of C. Then we have GU is equal to 0 again. C is still C1. Oh, absolutely the same. And finally, we reach the half. Now our half, this word, has some understanding and memory of what happened before. Because when you right now look at C right now saying plural. At the beginning, we have a, say, C equal like 1, and 1 means plural. And we haven't rewritten C. C is still carried out through our neural network. And at this time, when we need to make a decision, we know that we have information that the word that we saw at the beginning was plural. Again, maybe it's a little bit hard to understand, but C is actually called memory in this case. So what's happening, at each word, we can write a memory. Let's say right now we have a memory that it's plural. And then if the next word is not related in some sense with this word, students, we do not change, we do not touch this memory. This memory is still there. Then we have another word. This word machine has nothing to do with students. It doesn't, in this case, the gate will be 0. We have no updates. We still carry out our C through the system. And only when we see the word that is relevant to students, and it's for this word, it's important if it's plural or singular, we get our gate unit equal to 1, because the weights were trained in this manner. That weight will give us that if we see this particular word here, that means that this memory is important. And then that's exactly how we can remember things about the previous words when we make a decision if it's have or has, if our neural network makes a decision if it has or have. So, and technically speaking, C, this C vector, it's not only one, let's say, one element. It actually can be quite long vector containing a lot of, let's say, zeros and ones, like plural, singular, singular, plural, depending on which words we have seen during our progress. So for each word, we can create a new C. It can be created, and therefore we store a lot of information of the previous sentence structure when we reach even the end of the sentence. Is it clear more or less what's happening? So we create a new sort of memory unit. We have a new variable that we try to carry through the architecture with us. Is it more or less clear? Again, because then the next things, it's even more frustrating. Yeah, go ahead. Because it's learned, because our weights depend on inputs as well. They can depend on inputs, because when we train, probably it have seen the word students and the word have. And now, like it associated high weight for this connection and low weight to the connection between, let's say, students and has. So it's, again, this is all happens because we have these weights, because we train our model and we have these weights inside. So that's exactly how it knows. It's, again, it's really hard to imagine, but it actually happens in a nicely trained model. But we will see actually where the problem is, that it can remember. And this is another unit that is even more classical. It was proposed before GRU unit. It's called long short term memory unit. And now we have an even harder, even more complicated structure. Now you see A and C are different entities completely. So we carry the A's and we carry the C's on the top of them. And then we make a decision what to do with our memory depending on our input, depending on so-called forget gate, depending on our update gate, and depending on our output gate. So again, the thing is happens that right now we have another variable that we are carrying through the system, and its state of this variable, as you can see here, it depends on a current guess, but also on update gate and forget gate. So if we want to forget a previous value, this C will be multiplied by something very, very close to 0. And if because at the end you see sigmoid, and sigmoids are usually 0 and 1. It's very rarely that they're somewhere in between, because sigmoids are extremely nice function that looks like that. So you have 1 here and 0 here. So we right now have some so-called gates that helps us either to remember things or forget things from the past. And again, I will not go into details, but actually here you can see very fancy structure that maybe you saw somewhere in electrical engineering. If you look at this, come again? Digital, yes, exactly. So if you look at that, it exactly looks like that. So what you have right now, this is fantastic. So you have something like this is a gate, and you have this input that is going through that, and you have this input. And then if you stack them together, this line will be basically continuously going there. So your memory is continuously moving from one gate, from one unit, from one unit, yes, to another unit and to other. And then, depending on what's happening, you update this memory or you forget this memory. So again, this is hard to grasp. In order for that to work, you need to have a very good trained weights, like weights for update gate, forget gate, and output gate. But at the end, it shows that it can work. Again, that's quite fantastic. Yeah, and it's exactly the probably inspiration was from there. So, and this is a very standard thing. This is a super standard thing. You will see a lot if you go into RNNs, you will see a lot of LSTMs gates. They are very good to do these memory tasks. But what do we miss in all these things? And I give you a hint. What's the big difference between text and signal? Okay. Yes, but text also you can generate continuously. You can. ChatGPT is just generating the text until you stop it, more or less. But look at this scheme. So I give you another hint. Come on. In Signal, you don't have a information about future, but you have information about the past. In text, it's important to look in both directions. So all these things propagate from left to right. So the first word affects the second one, second and third one, never in return. And that's it's good for the signals, but it's actually quite bad for the text. So therefore, there is another architectures that they do something quite crazy. So you have system like that, and on the top of that you have a system that actually goes inverse. So it's so-called bidirectional recurrent neural networks, and in this case you have parameters A that actually A's that going from forward and backward, but again, I don't want to even to draw it. It's quite sophisticated looking, and to be honest, it's like if you're interested in that, you will see that. And also we can go deeper and we can create something like that, and that's actually quite common architecture. So you have actually, in this case, you need to have another index, let's say 0, 1, 2, and again, same here, 0, 1, 2, 0, 1, 2, and so on. So you have multiple layers in the vertical direction that will so because maybe to predict one output, you cannot just jump through one small unit. You need to have multiple units, and you go there. So it's also architectures that you can see. They're quite crazy, but you can see them. So, but in generally, the problems of RNNs, and I would like to end with RNNs because it's really hard to describe them. Honestly, you either look at the mathematics or you just do this hand waving. So they are sequential. That means that usually your processing happens word by word. And if it happens like that, you still have problems with the memory on long sentences. The big breakthrough of ChatGPT in particular was the ability to process whole paragraphs. So because at the end of paragraph, ChatGPT has absolutely good idea what happened at the beginning. RNNs, after 100 words, even with all these LSTM tricks, they will forget. So that's a problem. Another thing, due to sequential nature, it's really hard to parallelize it. It's really hard to run it on multiple GPUs, for instance, because it's really not trainable in this manner. So therefore, right now, I don't think that RNNs are very popular for applications. And finally, again, another reason associated with that, it's really slow to train. So RNNs played a very important role in the text translation in all these language models. But now, what do you think happens right now? What models replace them? Have you heard about new models from 2017, 18, and now, like DALL-E? Oh, not DALL-E, sorry, ChatGPT. What is that? What architecture ChatGPT? No, it's generative. It's more or less common, like umbrella term for anything that generates. So right now we have transformers. So it's called transformers, and this is not the same transformers, it's this transformers. Right now we have very complex systems, and I will just give you 2 slides about them, because when we go deeper and deeper into neural networks, it's harder and harder to really give you intuition behind them, because it's getting ridiculously complex task to do that. So now this is a classical example of a transformer, and what it's important to understand, we have this input embedding. Again, this is just a way to store the words. We have a very important thing here. I will talk about that in a second. And then we go through, this left part is called encoder, and right part is called decoder. And there is very interesting layer called multi-head attention. And again, in a couple of seconds, you will see that. And then again, you have this architecture. At the end, what's important, you have a linear layer, softmax, and again, output probabilities. It does absolutely the same things. It's just building these probabilities to see another word in the context of surrounding words. So, and the main really breakthroughs and innovations in the transformer models actually originate in 2 specific discoveries. One is called attention layer, and this is a paper from 2017. It's attention is all you need, and you already see that this paper has been cited 78,000 times. It's insane, because with this paper, complete revolution happens in the text generation and language models. So what makes this system really great? It's a positional encoding. Now, if you remember what we talked about when we talked about RNNs, we put these elements one by one inside of our units. But now the word order is stored in the data, and that's quite important. Right now, word order is getting processed before putting that into the neural network, and this symbol exactly represents positional encoding. So again, it's also hard to explain what's the problem here, what's the difference, but this is another way, much more efficient way to store the words and store the relationship between words in input data. And another thing, it's called attention layers. It's when words, again, if you try to explain it in a very simple terms, it's when the context of the word matters. So right now you are not looking at one word, you're looking at multiple words surrounding. So this is a very interesting example from one of the papers devoted to the translation. So you see on the top the English version. The agreement of the European Economic Area was signed in August 1992, dot, and then this end symbol. And on the left, you see the French translation of that. I don't speak French, so I would not even try to pronounce it. But the thing is, if you look at this plot, the brightness of the pixel shows the amount of attention the model is devoting to the surrounding words. So, for instance, when you translate European, it looks at European, but also it looks at economic. Okay, how it works. So, for instance, here you see la and there are completely like sort of, you just more or less directly translate la and there. But also it's important to define the gender to look at the word itself. You see, when you translate to la, what's important is to look at the area. And area in French is feminine. So that's exactly why you had translated it as la and probably not an L. Yeah, I'm not sure what in French would be. What would be in French masculine? How? Le? Okay, yeah, probably le. Oh yeah, I have no idea. So that's important. Right now, you do not translate ze directly to la. You look at the context. You look at the words around. And I think here it's a very also good example. So when you look at translate of zone, it looks both to economic and area, because zone has probably multiple meanings in French. So again, it's important to look at the context, and this is called attention. But the main sort of the progress and the main breakthrough happens when this model, I would not even explain that, was able to do so-called self-attention. If you, it can look at the sentence, and then you change the word order in the sentence even without translation, and it tries it. The model was able to sort of understand the internal structure and the grammar behind the sentences. So it learned the language similar to how we learn it. So we feel the grammar inside, we start to understand some relationship between words, and that's exactly what happened during the training of this model. This model, the transformers, were initially designed and developed to deal with the translations, but after basically 1 year, the researchers from Canada, from Toronto, and from Google, they realized the power of the model. And it right now it's basically the same model that is used in ChatGPT and all these things. It really can generate sentences. It can understand the structure of the text. And it's not important about how true the data generated by the model, but what's important that the text generated by the model is very, very accurate and grammatically correct, because the model can learn it by looking at the text. So yes, again, if you are interested in transformers, you can take a look on the internet. You can look at this Hugging Face website. You can even download some transformers and play with them. Right now, these modern models become so sophisticated that you really cannot teach them without going to a couple of lectures full with mathematics. But at the same time, I think if you are interested in that, you are more than capable of trying to do that and trying to understand them much deeper than I presented to them now, because that's a future of language models. If you're interested in something related to language, you must go there. It's without that, you will be quite useless on the market. So what have we learned today regarding the RNNs and transformers? So RNNs are quite good for processing of sequential data. It's my intention to say quite good because they are not perfect. In comparison with CNNs for the images, that really CNN, someone recently compared transformers with CNNs in the context of how big the influence of this architecture on the machine learning in general. So CNNs massively changed the landscape for the image or video recognition. Transformers completely revolutionized things on language models. So modification of RNNs with gated recurrent unit and long short-term memory units enable the ability to memorize or forget previous sequence inputs. For more demanding applications, one might use bidirectional RNNs or deep RNNs. RNNs have multiple disadvantages arising from the sequential nature of the architecture itself. And recent innovations in the text processing enables transformer architecture that demonstrates amazing results in the language models. So that's the last slide of the presentation. And before we leave, I would like to just spend, 5 minutes just briefly scrolling through this paper without stopping a lot on the text. I will upload it as usual in Ilias. But this paper is called Long Short-Term Memory. Again, that's exactly what we studied today for machine remaining life prediction. So when you have some complex machine. One of the important characteristics of this machine that you need to track is remaining life. It's usually called remaining useful life. Oh, sorry, why you didn't tell me that you see nothing? So this is it. So, and I just would like to show you a couple of pictures here, just so you see the current nature of RNNs, as each neuron output is dependent on the corresponding input as well as output from the previous step. So that's exactly what we discussed today. And what have they done? This unit that we saw today, it's quite massive, and this is also bidirectional things. That's thing that I was afraid to draw. That how it looks like. So you have you need to rotate it in this direction. So you have some units that goes from bottom to top, and some units that go from the top to bottom. And here the idea was to use degradation model generation to predict, based on the signal, the remaining useful life of the turbine, using the available NASA dataset that they generated on simulated data. And first, what researchers have done here, they took the data from the multiple sensors, like the temperature of the different, you see this is the sensors, fan section, the compressor section, combustion chamber, and turbine of the aircraft engine. Then what they did, they decided, okay, we will not process all the sensors independently. They trained a simple model just to output one value that they call health index. So depending on the health index, your engine either operating good or operating not so good. And then based on, they trained a degradation model using this bidirectional RNN in order to predict the remaining useful life based on the previous measurements. And again, I will skip this big part here. This is the raw data from the sensor, this total temperature at the different parts, low pressure and high pressure chambers of the engine. And by combining them, they get this health index that goes from 0 to 1. If you have close to 1, you are healthy. If 0, you're basically failing. And this is what I want to show you. They start to train recurrent model, and they actually failed quite spectacularly at the beginning, because if you look at the historic data until now, and then try to predict the remaining lifetime, they had a very bad results, honestly. And only when they had enough data and they looked that the curve starts to go a little bit down, their prediction, in this case this green line, gets much better. And again, at the end, they were able to predict in, let's say, 100 iterations forward that the remaining life would be 109 cycles, while in data it was 118. So they are very, very close. And again, this is very similar things. And the main conclusion that they made from that is that simulation results have shown that for the data set used from NASA, the bidirectional LSTM network has outperformed other commonly used machine learning techniques in terms of reducing the prediction error by over 2 flight cycles. So it was not actually big reduction, to be honest, but it was quite good. And future research will further investigate the effectiveness of this approach relative to other models. But I think this important thing that when they comment on the by comparison the predicted degradation curves with the real degradation curves, it is noted that the predicted curves have larger errors when the prediction is made using data from the early stage of flight cycles. So if you have not enough data, they actually failed to predict that. You need to have enough data, especially you need to have enough data that goes a little bit down in order to very nicely train this model, recurrent model that will be able to predict the remaining lifetime of your engine. So on that note, I think we have done with the recurrent neural networks. This topic, I think, is still quite interesting, but it's more or less history right now. So we will focus more on generation on the next lectures. Thank you.